Good afternoon, everyone. We are Team 17, and we're presenting our senior project today, the NISAT 1U Picosatellite. My name is Alvaro Quintero. My teammates are
Franco,
Obella, Rommel. The team mentor for the project was Dr. Shinde, and the faculty advisors were Dr. Hansel and Dr. Tosunoglu, Professor Tosunoglu. This is a quick overview of our project and what we're going to be discussing today. We're going to start with the introduction, which we already did. We're going to talk about the description and motivation behind our project. We're going to talk about the standards that we're using in the development of this project. Then we're going to discuss the different sections that we worked on, which are structure, thermal analysis, and the payload. And finally, we're going to discuss the parameters that we use for, or that we set up for Nexting for their testing of the satellite. So, first, the description of what is a 1U picosatellite. It is a small satellite that needs to measure at 10 centimeters by 10 centimeters by 10 centimeters, and the maximum weight of it cannot be larger than 1.03 kilograms. Our mission was to lay the foundation for the development of a 1U picosatellite and to continue the work that has been done in the Near Earth Explorer Hub from previous teams that have already been mentioned by NASA to be as candidates for a possible launch in the future. Next. Okay, so the related standards, the first standard that we're going to discuss is the CubeSat specification manual, which specifies all the mechanical, electrical, and operational requirements for picosatellites. The next standard we have there is a military standard used for the materials that can be applied to satellites and picosatellites. Third standard discusses all the processes involved in the development of picosatellites, and the last standard we have there involves everything regarding testing of these materials and the actual hardware under the actual mission conditions. Next.
Okay. Our 1U structure is made out of fiberglass. We chose this material since another teams have attempted to build a structure with fiberglass. These are constraints. Our actual weight is 0.482 kilograms, and the actual the font size competition is 1.33 kilograms. So we're good in the weight, and the center of gravity has to be 2 centimeters weight in the geometrical center. This is the mass and weights that we for all the components that are going to help inside the inner structure. And here is the properties that we use for analytical and simulation calculation for material for the fiberglass. Here are the equations that we use for the analytical values. Our assumption for this is that normal launching vehicle is 5 Gs, but we conducted at 10 Gs, all the calculations, just to have a better factor of safety. We assuming the worst position on the pivot launching vehicle, and then all the forces and all the resulting are going to be using for the simulation and single road and the whole structure, entire structure. Here we have the single road simulation for factor of safety. We fixed up everything on the bottom, and then we inputted a weight of 392 newtons on the analytical, and SolidWorks 392 newtons also. We have the different zeros here. Okay, we also did the static simulation for the whole structure. We fixture all the buttons in X, Y, and Z directions, and we apply a force of 98.1 newtons to each of the corners. That was the 392, we divided in 4. Okay, here is the complete structure results for displacement and strain. And then for the construction was straightforward. We just cut everything, all the pieces. We sanded all the parts to the length needed. And for the door, we created the channels in a mill. And then we use epoxy, which is used in aerospace companies. We have the 3D print inner structure. This structure is holding all the components, and the purpose was to have easy access, easy connection of the components. After we put all components on the simulation, we got a center of mass of right here. We have the results. We also did a compression test. This is our max load applied to the structure. As we can see in the chart here, the graph, we can see that we didn't reach a yielding point. And this is our final structure with the structure inside.
Okay, so we conducted a thermal analysis on our system, and we divided that thermal analysis into 3 different sections. And the first one was a sensor calibration. It was important to us to track the temperature inside of satellite to ensure that our system is not going to overheat or any of the components are going to overheat. We also know that our sensors, even though they're made by the same manufacturer, they will not have the same response. So we needed to actually test them and conduct a calibration behind those sensors. Okay, so how we did this calibration is that we expose our sensors to temperatures that we expect that our satellite is going to be facing once it's deployed in its mission. So we use a fridge to cold temperatures, and then we use a hot plate to expose it to higher temperatures. What we did is that we collect the steady state temperatures, and then we average them. After doing that, we went ahead and plot them in Excel and fitted the best line possible for each one of the sensors. And then using the equations that we obtained from those lines, we were able to adjust the program that was running the sensors, and it will give us better readings. Right? So as the first chart you see there to the right is data that was gathered before the calibration was done, and you can see there's a difference between the sensors of plus or minus 5 degrees of Celsius. And after our calibration of the sensors, we were able to reduce that gap to a difference of plus or minus 2. Okay, the next step on our thermal analysis was to analyze the heat generation inside our satellite. This was important because we don't want our system to overheat by the heat generation inside the satellite. And next. So how we conducted this is first we used data from a previous team who created ANSYS simulation of the Beagle board, and they applied the power requirements to each one of the main packages on the Beagle board, and they obtained they find out that one of the packages, the TPS package, is the one that generates the most heat, is reaching a steady state temperature of 77 degrees. So what we did for this analysis was to use our calibrated sensors to probe each one of these packages and do and actually track the temperature generation of these components under different load conditions. These are the results that we obtained. We did this at 2 different temperature settings, and there are 2 main things that we can point out from this analysis. And first, it is that even though there's a slight increase in temperature from the packages, this temperature is not high enough that it's posing a risk to our internal system yet. And the second thing is that the package that was singled out as the one generating the most heat during the simulations is actually not doing this in the actual physical test. So we are in communication with the team that is picking out this project afterwards in order for them to complete this test once again when all the systems are already connected to the Beagle bone and ensure that these parameters have no change and they're indeed the heat generation is not affecting our satellite. The last part that we did for our thermal analysis was the development of a thermal insulation layer for our system. Once again, we want to protect our internal components from overheating or to be exposed to solar radiation once it's deployed. The first thing that we did was to do a simulation of a thermal insulation layer with the same thickness and the same heat flux coming in, and we used different materials to see how they reacted. What we found out from this simulation is that aerogel, which has a higher thermal resistance, it actually has a higher outside temperature, an outer temperature, indicating that is indeed best candidate for as the insulation layer for a satellite. Once we knew that we wanted to use aerogel as our insulation, we went ahead and used one-dimensional thermal conduction equation to find out the appropriate thickness for the insulation layer. So what we did is that we established different scenarios, and we found out the thickness for each one of these scenarios. Since our main concern is for the satellite not to get overheated or actually radiation burn or components inside, we decided that the worst case scenario, when we have 100% solar radiation, was the appropriate thickness for insulation.
All right, so our mission description, so our satellite is going to conduct this mission from an orbit of 600 kilometers. And from there, it's going to be able to collect data from an atmosphere and be able to conduct cloud study and able to track tropical systems, as well as photograph oceans and vegetation and detect hazards to human life. All right, in order to accomplish this mission, we're going to have you have a determined payload subsystem, which includes a through-the-lens camera and a compound optical system. This system is an optimization from a single-lens system developed by a previous team, but this single-lens system would have proved too large to fit inside a 1U satellite. So some of the benefits of using a compound optical system is that we can, by combining lens power, we can get greater magnification, and therefore we can decrease the focal length and overall system size. Also, by combining achromatic lenses, we can reduce chromatic aberration. So this is some of the important formulas, in order to determine all the paraxial values and parameters. This is the magnification formula, and the lens formula was applied to each individual lens in order to determine the focal length of the system. So, in order to determine our image height, which is our sensor height, we determined the number of pixels, and from there we found the total pixel area, and that was plugged into this equation in order to find the image height. And then we used the lens equation to determine again the focal length, and then we were able to find the total magnification of our system. Here's the results from these calculations, and we see the image height of 2.68, and these are all our parameters, our triple compounding calculations for an object height of 25 kilometers. Then we went ahead and we conducted a simulation for the system, and a program called Windows 3D Basic, and these are the results that we have from the simulation, which are very similar actually to our analytical values. And so our optical system was able to reduce the overall size of the previous design by 47.2% and increase its magnification by 42.3%, and this was done by doing a triple compound system. So our manufacturing of our optical system we used Edmond optical lenses, and then we utilized fiberglass, and we also coated the optical tube with light absorbent optical coating. So for our optical testing, we were able to reduce the scale from 600 kilometers to 6 meters, and that reduced our object height from 25 kilometers to 25 centimeters. This is our optical testing setup, and from here we have the image, which we can clearly see here. The 1/4 is a quarter of a meter, which is a 25 centimeter object height.
So one of the important systems for the for the satellite is to make sure that all the components is going to be previously tested. So we're going to conduct a balloon launch system to make sure that the component is not going to fail. This method is selected because of the degree of cost and effectiveness, Also, we did a balloon performance calculation and a drop test to ensure that the integrity of the structure will stay safe as hitting the ground. This is the balloon performance calculation. We are looking for the how high is gonna raise the satellite without the maximum flight load. Those are the calculations. Those are the equations needed for those values. Also, we need, after we obtain the height on the satellite, we need to do a parachute calculation and the impact force that is gonna, with the impact force, they're gonna hit the ground. So with this, we obtain the required parachute of the requirement diameter is gonna be 2.0 for our satellite. So this is gonna conduct a total force of 4.225 newtons. For the drop test, we have to make sure that the integrity of the structure stays intact after hitting the ground. So we did 3 different scenarios, and we were calculating the impact force for this structure. These are the 3 different scenarios, 3 different foam, and 3 different heights. So those are the forces that we were obtaining. So they are really close to each other. As a club, we agreed to spend up to $1,000 as a budget. So up to now, we spent $478 for the satellite. For our Gantt chart, we start on August. So up to now, we complete all the requirements for the satellite. So for next future works, we need to integrate the communication system. We need to put the power system and the altitude control system. Also, we need to, for the thermal insulation, the insulation layer needs to go under vacuum chamber testing. And for next thing, they're gonna conduct the high altitude weather balloon testing.
Thank you very much. Now we're open to any questions or comments that you have a lot of questions.
Question I have is on drop test. With all of the optics and everything in the system, did you do any simulation work to understand the impact effect of the structure to the components inside? Because I would assume that they potentially, if they're not in there tight, you could end up having one accelerate versus the other have impact internally.
Yeah, actually we also need to perform vibration testing, and for that, which we haven't been able to do it yet, but it's under consideration, and we have proposed it to student teams within the club to do it.
Okay, and being fiberglass, this is part of the reason I even asked the question. Structurally, that's not quite as stiff as typical metal structures you'd be using. So you're going to get a situation where you get a rebound and a recoil response.
Well, we actually, he went over that section where we put the system on a compression test. And
that's static though, basically. That's not under impact. That's not a high,
Okay.
That's the issue with that approach.
Well, we were able to find out that at a pretty high compression, you're totally right, it's not the same. But we weren't able to find a yielding point, so we're not finding any deformation in our system. And so, yeah, that's something that we have to note, and we have to relate to the teams coming up to make sure that they complete a complete analysis for the drop test with simulations and with the actual physical testing.
What about fracture toughness?
For fracture, the numbers, we did the simulations and we did the analytical calculations for structure, and we didn't see, we have a factor of safety of around 81. So as of now, we're not thinking that it's gonna, the maximum launching force that we're thinking is about 392 meters.
Yeah, launching isn't the issue, it's landing, I think.
Yeah, well,
'Cause
yes.
The loading in a balloon going up is not anywhere near
Yeah,
what the
well,
response is.
we're reducing that impact force by applying the parachute, and we do have the impact velocity. So we will have to use those parameters and put them into our simulations to get the answer you're looking for.
Okay, thank you.
Go ahead.
I have a question and a comment. Whenever you use averages, list your standard deviations. Just because we don't, or at least I don't understand, your average could be
Different.
on point, but your spread is well enough where the data is telling you something different than what you're using that data for. Second, when you were building the fiberglass, I'm hoping you guys use proper color protection.
We have respirator, we have gloves, we have goggles. If you have access to the manual, we have. No, I'm not saying. I'm just saying that everything was.
Especially for the construction of the tube, which we made from the fiberglass cloth, and we applied the epoxy. So definitely you need to have a really good respirator and be able to wear very nice quality clothes for that.
When we were sanding and trying to get the tolerances that we were looking for, the dust was pretty intense, and we were instructed by Professor Ciccarelli in the manufacturing lab to make sure that before we did anything, to have proper PPE, safety goggles, gloves, respirator.
Thank you.
Any other questions?
Is it required that the stress is only in one direction?
Well, yeah, since when we're launching this, it's gonna go straight up, so we're assuming that our forces are acting thoroughly perpendicular to the structure, straight down on the structure.